Welcome to a new interview with Jie You, where we're going to be talking about Zeus, which is a framework for understanding and optimizing GPU energy consumption for DNN training. As always, the link to the paper is in the description, and I hope you enjoy our discussion.
Hi, today we're discussing a paper called Zeus that focuses on understanding and optimizing GPU energy consumption for DNN training. And the energy consumption for DNN training is getting increasingly high due to recent advances on large language models especially. And also, NVIDIA is building GPUs that has more and more power specifications as well, to a point that nowadays we can't even we are holding back by the amount of energy that can be provided to data centers to build large AI clusters. And to give you some perspectives, even before this AI boom, the IT industry is already consuming 7 to 8% of global electricity today. And it was projected to hike up about 10 to 14% by 2030. And with the current Gen AI boom, it is reported that, for instance, Amazon consumes 11.9 gigawatt hours to just train one large language models. And this amount is equal to more than 1,000 average US households, and average US household is on the higher end of energy consumption.
Mm-hmm.
And
maybe if I can jump in there before we go to the next one. I noticed in the paper you referenced, I think, GPT-3 and the power consumption used to train that one. Do you know in recent incarnations of these models whether this amount is increasing rapidly or not? So the new large language models that are coming out now, are they exponentially getting more expensive to train as well, or are they kind of at a fixed expense threshold? Let's say.
Yeah, they're exponentially getting more energy demanding because the amount of GPUs that are used to training is increasing. So yes, it is increasing rapidly, especially recently with the Gen AI boom.
Okay.
Yeah, and what makes it worse is that a lot of the times after we train the model, we are not done yet. The models would need to be periodically retrained to keep it refreshed, and so these big numbers of energy consumption for machine learning training are not very likely to decrease on their own at the moment. And so how do we solve this problem? Can we just solve it with getting better hardware? After all, NVIDIA every year when they launch new hardwares, they may be produced with better fabrication process and slightly more energy efficient. Yes, it does help a little bit, but older hardware still stick around because getting new GPUs doesn't mean we're deprecating the old ones. And also, switching GPUs means some migration cost. And so a more tangible solution is to see if we can have a software solution such that even if when we are using the last generation of hardware that are not the most energy efficient, we can still bring efficiency wins. And more importantly, the efficiency wins or the energy savings that we bring can be hardware agnostic. And so in this paper, we first start with understanding the GPU and energy consumption. And by that, we first define the energy consumption. And our take is what we call energy to accuracy. This is defined as the energy consumed until the neural network reaches target validation accuracy specified by the user. And we can further break it down to be the amount of time we need to train until the certain validation accuracy, TTA, time to accuracy, multiplied by the average power that the entire training cluster use. And the TTA, time to accuracy, can be further broken down into the amount of epochs or iterations, mini batches, that are required for the model to converge, multiplied by the epoch time, which is the interval of between each epoch. And we noticed that there are potentially two knobs. One is the configuration of the job itself. Another one is the configuration of the GPU power config that may affect all these three parts of that consist of the ETA. And one is the batch size, because when we are training the large language model, training any DNN models, we train in using some kind of in a mini batch fashion. And by increasing the batch size, a lot of the times we get a slightly higher throughput, as in the training speed is slightly higher. And so each epoch takes a little bit less time, but also it increases the amount of power for average power consumption for the GPU, because the GPU need to process a bit more data every batch. And the GPU power limit also affects these two, the epoch time and average power, because the GPU power limit is basically a power wall that can be applied to, for instance, NVIDIA GPU. And when we reduce that, the average power of the training process would be lower, intuitively. But also it may slow down the GPU and make the epoch time longer.
Mm-hmm. I have a number of questions on this particular choice of metrics for tuning.
Mm-hmm.
Are there other parameters that we could have picked rather than batch size and power limit? Like, if you had to do this study again and you got to pick other parameters besides these, are there any other ones that come to mind that you perhaps considered in the preparation?
Yes, good question. So there are other things that we can tune. For instance, we can change the architecture of the network and apply some other, like we can make the network smaller to just use fewer number of GPUs for training. But for this work, when at that time we were trying to make it network agnostic as well. So we want to search for generic options that can be applied for many scenarios. So we didn't pursue that direction. Yeah.
Mm-hmm. And are there any other? So I agree that being network agnostic makes a lot of sense. Are there any other parameters that are also network agnostics that you could have considered? So I only remember vaguely, but I think there was a reference in the paper to other, let's say, power related parameters that you could set on the GPU side as well. I think there was something under discussion. I don't recall exactly,
Yes,
but
yes. So power limit can be further so power limit is a more generic knob. So for GPU power configuration, and NVIDIA actually do allow you to change the of some more fine-grained knobs, such as frequency itself, for and it can be tuned independently for the memory and the compute for GPU, the VRAM and the SM frequency. Clock rate, basically. And also you can even tune the power, like the voltage offsets, to some extent, that you will be, some very hardcore gamers, they overclock their GPU and they tune this very, enthusiastically. And we didn't go into that, and because we want our solution. So with introducing more knobs, the amount of search space also increased dramatically. And so that's why we were choosing power limit, which is sort of like a proxy knob for all the underlying GPU power configuration knobs.
Yeah, understood. Another question I would have is when it comes to the batch size. So we mentioned that an increased batch size, we would have lower number of epochs, and hence speed up or have fewer iterations in this formula, but that would be compensated to some extent by a higher average power.
Yeah.
Do you have some intuition for how those terms relate to each other when we increase the batch size? Because you have a diminishing effect from one side and then an increasing effect from the other. And whether or not your ETA would be improved as a consequence depends on how those relate to each other, right? Do you have a view of how the batch size affects the power compared to the number of epochs? Is that something that's I don't know, that other people have done studies on or similar?
In the paper, in the appendix of paper, we have a detailed like a parameter sweep of the influence of batch size for different workloads.
Okay.
Yeah. So I think we can refer to that. And yeah.
Okay, very good. Thanks.
Okay, I'll move on to the next slide. Oh, and also one thing that I want to mention is that batch size actually also affects the number of epochs needed for training, because the batch size, changing the batch size not only has effect on the throughput and energy itself, it also has the effect of the the model's training curve, or how the model generalizes, how the model converges. So, and it is worth noting that so this is the between the batch size and power limit, this is the only knob that also affects the that affects the number of epochs. Yeah. And so our observation is that in common practice, neither are optimally set when we're running models without tuning it. And I'll elaborate a bit more in this slide. So we tried sweeping the entire 2D space of the configuration grid for power limit and batch size. Effectively, we trained with almost every possible configuration, and we computed the time to accuracy and the energy to accuracy for one model. This is one DeepSpeech 2 model trained on NVIDIA V100 GPU. And I'll plot the default value that people would, if they don't tune anything, would be using here in the triangle. And the default value, which is the original batch size from the original paper and default power limit of NVIDIA GPUs. And we can see that the default is not ideal because on this chart, the closer to the left and the bottom are better, right? And then after we perform such parameter sweep, we can find a clear Pareto front of efficient energy and time to accuracy pairs. If we zoom into this Pareto front, these Pareto front are basically sets of configurations of batch size and power limit pairs. And we can learn that these knobs can be different. So, and there's no very monotonic pattern of, which side is choosing this would be strictly better than that. And so it's kind of, you can see sometimes bigger batch size is better, like sometimes lower batch size is better. It all depends on your objective. And more importantly, this Pareto front, the curve shows a trade-off between the training time and training energy. So you cannot, if you want to reduce energy, sometimes you have to sacrifice the training time and vice versa. So in the past, people always have been optimizing for the training time to make the model train faster, to make it converge faster. But inevitably, it may cost more energy to train.
Do you have a view on how this graph would change if we train the same network on another set of data? Does the data affect what the Pareto front looks like?
Yeah, great question. So data, the Pareto front is more or less agnostic to data because the data is itself is large distribution of different samples. However, there are studies of to create adverse samples to blow the energy consumption. So the energy consumption training so the energy consumption is slightly related with the data, but if we use but it's not very much significantly impacted by the data we use.
Mm-hmm.
If that makes sense.
But it is significantly impacted by the. Yeah, sorry. Go ahead.
Yeah, but it's significantly impacted by the knobs of the GPU and the model parameters such as batch size. But if we craft the samples to be artificial samples, then the energy can be influenced.
Okay.
Yeah. And so now with this Pareto front and with two knobs that we are looking at tuning, we want to reduce our multi-objective optimization problem down to a single objective that more tractable, right? So we define a cost of training as a combination of the ETA and the TTA by introducing coefficient eta. And so basically the user, depending on their preferences, wanting the model to train faster or wanting the model to be more environmentally friendly, the user can set the eta accordingly. And with this, so in the following discussion of the paper, when we're referring to training cost, we'll be referring to this cost metric, that is a combination of ETA and TTA. And the goal of Zeus is to automatically tune batch size from whatever the default is to the point that the cost is minimized. So we want to basically start from default, and we want to hit a Pareto front, and also we want to hit the right point of the Pareto front. However, this is no easy problem. We can see the Pareto front here because we already brute force train every possible combination and combination of the configs. In reality, training each takes hours or even days. In the end, we defined essentially now we define ourselves a challenging optimization problem. So how do we navigate this search space? A key insight that we found that is that the optimization for the batch size and power limit can be decoupled by the following strategy. So we can find the best batch size across retraining jobs because jobs get periodically retrained a lot of time, and we can find the best power limit for one batch size during training because in the next few slides I'll elaborate more. And at a high level, we leverage framework called multi-armed bandit to be able to learn a stochastic function from batch size to cost. And this formulation automatically trades off exploration and exploitation so that we can efficiently search the space without wasting too much energy. And note that the cost is again the combination of ETA and TTA.
Mm-hmm.
Yeah. So now let's dive into the technical side of how we solve the problem in this paper. And right before that, we want to show. Let's take a look at the potential of energy saving. So if we have optimal config, how much we can save for different models. And in the paper, we started 6 different DNNs, and we for plotting this chart, we were running grid search parameter sweep to essentially sweep the entire search space and find the best configuration. And so we normalize the energy by the default configuration's energy, and we found that in many cases the default unideal, And in extreme cases, for models, we can, with optimal configuration of both knobs, we can achieve up to 75% energy reduction for training. And so sometimes, and you can see that both knobs are important, because when we tune both knobs, when we set the best of the both, it always outperforms it's always the most performing in terms of energy efficiency.
Mhm. When we do a grid search on this, how fine grained do we define our grid to be? So I guess we discretize the power and the batch size. I mean, the batch size is already discretized to some extent, but how large of a grid are we evaluating?
Yeah. So I think we were evaluating the power in terms of the granularity of power was 50 watts or 25 watts, and the batch size is the batch size usually has to be power of 2, so we're having limited choices in the batch size used, and it varies from model, the granularity of the batch size.
Mhm. Okay.
Yeah. So let's discuss the challenges of this approach. It all boils down to the fact that the ETA is very difficult to determine, and because each of these components are kind of having a nonlinear relationship with all the underlying knobs, and they also sometimes interact with each other. And the reason is in intuition is that the GPU is a black box. It's proprietary hardware architecture by NVIDIA, and the NVIDIA itself has provided internal some underlying voltage frequency control algorithm called the DVFS that are actually that tries to find the best voltage and frequency given some certain power and some power limit config. And that algorithm itself is also unknown. And therefore, what it means is that model the power consumption for GPU is very much not impractical. There has been previous works of doing, power modeling for general computing, any kind of chip, CPU and GPU. They require extensive offline profiling and more, but the downside, it cannot be avoided, that is that it cannot really generalize, because profiling itself, when we change the model, we need to profile again. And there also has been some power simulations and for to calculate the GPU power consumption given, say, a workload, but the accuracy is and also generalizability is a concern. And with new generations of GPUs, they get released every year, every few years. This method does not scale.
Maybe one follow-up questions on the internal voltage and frequency control algorithm.
Yeah.
So I'm jumping ahead a little bit, but I think in the multi-arm bandit approach that you're taking, you're modeling the different combinations of batch size and then power limit as like having some mean and some variance. And you're assuming those to be static in time, right?
Yes.
Is that a fair assumption, given that you have some form of internal control algorithm? Do you know whether or not that's a good approximation or not?
Yeah, great question. So the frequency voltage control algorithm is operating at very finer granularity, in temporal granularity. So it can change the frequency and voltage of the GPU depending on whether there's active compute going on, and at this moment, but in the multi-arm bandit abstraction, we were whenever we observe how much energy we are consuming, whenever we do profiling, the profiling window is much bigger than the DVFS kind of adjustment frequency. So so we reasonably sort of denoised this DVFS dynamics of the DVFS itself. Yeah.
Okay. One final follow-up question on this as well is, did you notice that the buckets with a very high power limit, that they ended up doing the same thing? So if you have one batch size, let's say we keep that fixed and then you vary the power limit, but you always have the power limit in a very high domain. Do you notice that the results come out to be close to identical? My reasoning here is if you have some internal algorithm that sets the voltage and frequency, maybe it caps it already quite a lot before the power limit. Is that something you observed?
Yes, good question. So depends on the model. Like some models, if the model training, like even if you set power limit to 200 watts, it max out at 50 watt. Then setting it further to say 300 watt power limit, it won't make much difference. So it is true, like the power, you get some diminishing sensitivity on the power limit if the model is if the model does not consume too much power.
Okay, thanks.
The next challenge is the time to accuracy is also very difficult to track because this is more innate to the training itself. Messing with the knobs such as batch size affects the model's accuracy in unpredictable way. There has been numerous studies from theoretical machine learning to more empirical studies of how to best pick the batch size, and and people like it's a very the relationship is very complicated, like complex. And what it makes even more difficult is that the training itself is stochastic because there are random variables introduced for the training. It's never deterministic. And because we initialize the parameters in different ways, and between batches, we shuffle the samples of the training samples. So even when we're training with the same config, the time to accuracy would change every time. And so these two challenges are what we need to be aware of, and we are what we solve in our DNN optimization energy optimization framework Zeus. We want to make it generic to be able to optimize the cost for arbitrary DNN model and arbitrary GPU type. And also we want to make our energy optimization not too energy demanding. Like if we were exploring suboptimal energy, like during our exploration, we'll inevitably be training with suboptimal energy configs, and we don't want to spend too much time in that suboptimal energy config. And more importantly, we want our solution to be practical so that we don't want to have offline profiling. And this is because when solutions like this are deployed in production, the models are always changing. So all the models that are trained, people don't train the same model on the same data again. There's no practical use for that. People always mutate their models or mutate their data, trying to find, trying to achieve better model accuracy, right? So offline profiling does not really work in that sense. And we also want our solution to be not impacting the model's convergence, the model's accuracy. The overall workflow of our system is that, so first of all, we have very basic components. Everything is trained on the GPU, and there is some training framework or deep learning execution engine, and such as PyTorch. And NVML is a library that NVIDIA provides for tuning the power configs of GPU. And on top of that, we add our framework Zeus, which takes in jobs of training. And note that because in practical settings, jobs can usually get retrained, and these retrained jobs each time provides opportunity for exploration. And when jobs are submitted, we perform a search of we perform optimizations of power limit as well as batch size. And during the training itself, we the DNN training config and the GPU power config are feed into these two, the NVML and the DL execution engine respectively. And we observe metrics such as GM power stats as well as DN training stats such as the accuracy curve. And our Zeus takes in these feedbacks, adjusts the configs in an online fashion. And
One follow-up question on the retraining of jobs. In what scenarios do you usually encounter that retraining? Do you have that pretty much in all kinds of DNN training, or is it something more specific, like more specific application areas? Because I'm assuming that the jobs that you have in the list at the top now are really identical jobs that you would feed the model. And I guess a lot of the benefits from Zeus also comes from the assumption that we have a set of jobs that are identical.
Yes. It's pretty common. There are papers mentioning that in production settings, how frequently job retraining are happening, and the intuition is that models trained on so data is always evolving as well, and the model needs to be refreshed on the new data, and to keep up the model accuracy, and that's usually the driving factor of why models are getting retrained.
Mm-hmm. And so when we say that we do a retraining job, we don't necessarily require that the same data is involved. It can be different data, just that we have the same GPU architecture and the same network. Is that the requirement for it to be classified as a retraining job, or what do we exactly consider in that category?
You're right. The job with different data and the same model with different data can still be considered retraining job. Yeah.
Okay, understood. Thanks.
And so, the power limit optimizer and the batch size optimizer, they working. So I'll discuss how they work in the next few slides. The key idea is we want to decouple this optimization of batch size and power limit so that we can search them individually, and we don't to reduce the dimension of searching basically. And the idea is that the batch size, the relationship between the epochs and the batch size are random and intractable, but the relationship between the power limit and average power are pretty much linear and deterministic. Not linear, but monotonic, and so the idea that we adopt is that we use batch size optimizer to fix the batch size, and then given the fixed batch size, we can sweep the power limit at runtime for a given job, and to find the best power limit, and then we can think of this optimization as a nested loop. So the power limit search is in the inner loop, and the batch size search can be in the outer loop, and it's still a valid. Like still can find the optimal because of this decoupling. This decoupling idea.
So are you saying that, correct me if I'm wrong here, but are you saying that for a given batch size, you always have the same optimal power limit?
Yes, that is true. Yes.
Okay.
And more importantly, the power limit. So because the DNN training is recurring, DNN training is a periodic thing. So we train batch after batches, right? And so for finding the optimal power limit, we don't need to train the entire job end to end. we can perform parameter sweep for just the beginning part, say the beginning few hundred iterations of the model, and we can still, and the best power limit that we find for that first 100 iterations can be applied to the entire training. So because training is in an iterative fashion after all. And that's why we're able to perform this power limit search in an online fashion. We don't have to we don't have to profile offline. We can do it online. And even if we do it online, we wouldn't be stuck in a suboptimal power config for too long because all the search will be done in the beginning of the training. And then after that, the entire training process will be using an optimal power limit. That's the key idea for this nested loop design. And we call this just-in-time online profiler. We basically provide the power and throughput of each power limit. And we found out that as low as 5 seconds of profiling for the beginning of the training is enough. And this reduces the overhead of the profiling. So because we key idea is first, we only need to profile once for each batch size. The optimal power limit for the given batch size is fixed, it's constant, and the profiling only takes very small amount of time comparing to the entire training process. And the profiling result, the optimal power limit can be will improve the power for the entire training process. And next, we move on to the batch size optimization, which is harder because the relationship between the epoch and batch size are very random. And so we highlight that a good solution must incorporate the stochasticity of DNN training because there are many random factors that are involved. And also, during our search of batch size, we don't want to spend too much time. We don't want to spend too much resource stuck exploring a bad batch size. So we want to intelligently trade off exploration and exploitation. And this the idea of how to explore and how to balance exploration and exploitation in an efficient manner naturally lead us to the multi-unbounded solution. So the multi-unbounded is a framework that has been proposed to solve many kind of optimization problems, and the objective function is always I want to balance the trade-off between exploration and exploitation. And also multi-unbounded, it itself models the stochasticity in it. So it's a perfect fit for our batch size optimizer. If we take an example of multi-unbounded, there are many different implementations of variants of multi-unbounded. We focus on one of the classic ones called using Thompson sampling. The idea is that each arm of this multi-unbounded corresponds to one of the config that we want to search. And with this config, there is a cost function distribution because it's stochastic as after all. And each time we run, it will be given observation of this distribution using this config. And we are trying to estimate this distribution function and also trying to balance the exploration and exploitation in this process. So each time we have an observation, we would refine the distribution of this training cost, basically. And so the idea is that for each job occurrence, we sample the expected mean cost from each arm. We select the arm with the smallest sampled mean cost. And we run the job with this config, and we observe the cost of this arm. And we update the arm's distribution using some statistic tools such as Bayes rule.
So if I understand correct, once you select then a batch size, you run the entire job from start to finish on that batch size and then update with one. Okay.
Yes. Understood. So we keep the batch size constant. And
Yeah.
the reason is that, so we want to, if we change the batch size during the training, it changes the model accuracy itself. We don't want to introduce to like additional noise to the model accuracy itself.
Mhm. Okay, and I guess that's the key for the decoupling, that you can alter the power limit within one training set, and then you can do a
Yes,
sweep as you're training. But for the batch size, you need to have that fixed on well as you're starting your training.
yes, exactly. Yeah.
Okay.
And we also add some extensions to this multi-embedded formulation to make it more efficient. And also make it adapt to our distributed like machine learning training scenarios. So one thing is, should we run suboptimal batch size until completion? The short answer is no. So we want to apply something like early stopping when we run a batch size that are very suboptimal. When we observe that, and when we have enough confidence, we kill this job immediately, and start with new. Start with another config. And what if batch size never converges? So sometimes batch size, if it's too large or too small, the model just would not converge. We don't we would eliminate those kind of batch size configurations as well. And so sometimes in the production settings, there might be multiple concurrent job running. So if a new job is submitted and we need to pick a config even before we have the observation of the last trial run, what do we do? Like Thompson sampling, the framework Thompson sampling can actually handle that natively, so we don't lose exploration efficiency with this kind of concurrent job submissions. And let's visualize the searching of using Zeus in action, and we compare it with grid search here, for example. So using a grid search, we have to sweep across all the combination of primary config knobs, and finally we'll pick the best one. And so with Zeus, the search is a lot more efficient. We hit the best one much faster. Yeah, and we and in you can see that like the trajectory is taking a lot less iterations here.
So how come if I
Yeah.
try to if we can go back to the figure on the last slide,
Mhm.
if I try to understand the figure that we have for Zeus, it looks to me like we're picking some batch sizes, but we're not doing a sweep of the power limit for those. Because if we did a sweep across the power limit, let's say we pick a batch size of 96, and then we do a
Yeah,
power limit sweep, I would expect there to be an orange line covering from top to bottom in this figure. So are we saying that we're keeping the power limit fixed for these, or I don't quite understand what we're seeing.
yeah. Great question. So this is because we did sweep the power limit, but that is limited to the first few iterations of the training, and later we are using optimal power limit for this batch size for the entire training already, and that's why you don't see the like sweep of power limit. So the because of the decoupling of batch size optimization and power limit optimization, basically given a batch size, if we see the batch size only are like we're hitting power limit, a certain power limit, that means we are like using a certain power limit. We actually did sweep all the power limits, but that is only in the very beginning of the training. And then
Okay, so yeah, sorry. Yeah, so in effect, then you're only doing one, more or less one full scale training, or maybe more if you're exploring that same batch size multiple times. But assuming you only stop there one time for the batch size, you only do that with one power limit, and then there's only one point in this grid being filled with the orange line as a
yes,
consequence.
yes.
Okay.
Um,
Okay, understood.
yeah. And so in our evaluation, we were using 6 different neural networks, and we also ran that across multiple different GPU hardwares. and
Just
our
one, yeah. Sorry, one question that just came to mind as well on the previous picture.
Mhm.
Like this one exactly. Could you not do the same? So in the grid search, could you not just do the same sweep for power limits in the grid search as well, and drastically improve the efficiency there? Because just as we said in the case of Zeus, we have one optimal power limit for any given batch size, and in the power limit, we're doing a grid search really of all configurations. But could we not do a sweep for each batch size in the grid search and do like a modified grid search that's a lot more efficient?
You can, yes, indeed you can. Good point.
Okay, cool.
So for the evaluation we used these kind of neural networks and the GPU architectures, and so overall we found that comparing to the default value, we have higher we are more efficient in terms of the power. Energy saving can be from up to 76%. And we also found that if we change the eta of the cost function, we can use this framework to optimize the training time as well, and we can achieve like up to 60% training time reduction. And note that some of the bars here in this chart, we are worse than the baseline, and that is because the baseline is already optimized for the time. And in the next part of the discussion, I want to share some of the follow-up works of this paper from our lab and also from our lab mate. We extended this. So with the publication of the paper, we open sourced our code immediately, but later we also extend our open source framework to be, to counter the, to help more people perform energy measurement as well as optimization. And we want the framework to become the go-to framework for deep learning energy measurement and optimization. And currently, we already have a lot of Docker pools and a lot of stars on this repo. And we want to be able to capture two sides simultaneously. One is better energy measurement attribution and monitoring for DNN training, so that you can plug in this framework into PyTorch your training jobs and observe how much energy you're consuming. And also we want to make it like very easy to use open box like energy optimizer for you. And these components like that we provide in this open source framework can be composed just under user script, depending on what your application needs. And as of this year's April, we already exceed 100K pools in Dockers. Yeah. So we can take a brief. Let me take some time to briefly show you how we can use Zeus with your code. How it can be used. It's pretty simple. So the core API for this measurement is called Zeus Monitor, which basically lets you measure time energy for arbitrary code ranges. On the right is just a typical training loop in PyTorch. And you can simply import our library and give it the list of GPU indices to keep track of if you have multiple GPUs. And then you can mark the range of code you want to monitor. For instance, if you want to monitor for the entire training, you can do that before the training loop and after the training loop. Or you can add it for each epoch and have a more fine-grained measurement. And you will find the energy measurement here, like with the return of the monitor and window.
One question on the parameters that you specify when defining your monitor parameter. So you have GPU indices list, as you mentioned before. Is that if you have multiple different architectures of your GPU, or what is that for? Like, is
Uh,
Zeus compatible with different? Because I'm assuming in the context of the discussion that we had up until this point that we're talking about one GPU or potentially a cluster of GPUs of the same type.
yes.
But this parameter, is that something that well, allows us to use multiple different kinds of GPUs at the same time and still optimize for it? Or what is the purpose behind that one?
Yeah, great question. So the current purpose for this one is just to select like which GPUs we are monitoring, because sometimes you have a cluster running multiple jobs, or you're not using all the GPUs for this particular job. So that's why in this job you can specify that, okay, this job I know is going to use a GPU 0, 1, 2, 3. So I specify here. So it has an accurate accounting. And you're also asking an interesting question about like whether if we are training with heterogeneous GPUs, different type of GPUs, what would happen, right? It's a great question. So for this open source framework, I don't exactly know whether it supports heterogeneous GPU clusters. Heterogeneous GPU clusters, in the first place, it's not a very common approach at the moment. But I actually do think that our Zeus monitor would be able to support heterogeneous GPU, because even when we're not using heterogeneous GPU, the energy for each GPUs would be varying already, and we measure the GPU. Oh, sorry, we measured energy for them independently already. So I would assume that our current framework would already support heterogeneous GPU.
Mm-hmm.
Yeah.
Okay. And maybe a follow-up question in the case of homogeneous GPU clusters.
Mm-hmm.
For multiple GPUs
Yeah.
in the same fabrication line, the same architecture, do
Mm-hmm.
they always behave the same given the same power limit and the same batch size? Like, do you see the same results if you take two seemingly identical GPUs, but that are nevertheless not the same GPU?
I see your point. I see your point. So, the TLDR is that they still can vary, and the range of the variance are small, but they can still vary due to different GPUs have different. Basically, each GPU consists of a set of chips, right? And the most power hungry chip is the GPU core, and the GPU core, due to the fabrication process, it can have varying, like some GPU cores need a higher voltage in order to not be faulty, basically, like.
Mm-hmm.
And so it can be more power hungry, and so there are some variance in the GPU chips as well, but the variance range usually is small.
Okay, so it's not noticeable in the context of trying to find the best batch size and power limit.
Not that we have observed.
Okay, thanks.
Okay. Yeah, and with the monitoring, like with the Zeus monitor, we're able to measure now. And next, I'm going to show how we add our optimizers in your training loop. And so the power limit optimizer, as we mentioned before, automatically profiles and then pick the optimal power limit during training. You can import the power limit optimizer and pass it as an instance of the Zeus monitor, so that it can measure and measure the. You can pass in the monitor to the optimizer, so it can, you can hook into the monitor and measure energy through that. Next, you need to let the power limit optimizer know that, okay, we are here, we are starting a new epoch, and here we are finishing one epoch. It's very much like Hugging Face trainer callbacks. The we simply adding some hooks to the training loop, and the power limit optimizer will take care of everything, and the automatic profile will optimize the power. As simple as that. And also, we allow the use of different policies of the optimization itself. The user can define the metrics of their optimality, And as long as, like, for instance, maybe you're fine with training it like in a slower speed. As long as your training is done by tomorrow morning, you're fine. You can tell the optimizer to, like, okay, I really want it to be energy efficient. And or in some other cases, you value the jobs like finish time a bit more. You can put in a different config. Yeah. So these two libraries are, as you see, are very they can be plugged into a training script and pretty easy to use. Aside from that, we also using this Zeus monitor, we created a ML energy leaderboard. Basically, we ran a bunch of models, perform energy profiling, and across different GPUs, and we report them. And this is, to our knowledge, the world's first open source performance energy benchmark for LM text generation models. And we benchmarked the inference energy consumption as well for more than 20 recent LLMs in terms of their latency, their throughput, and energy. And also we profile different NLP datasets. To date, this is the largest and most comprehensive open source energy benchmark for all the publicly available LLMs. And at the time when we were writing the paper, LLM was not as popular as today. But after that, as we all see, the Gen AI trend took off, and that's why our leaderboard, the focus shifted a lot on to LLMs. Both because LLM is recent and a lot of people are focusing on it, but also because LLMs tends to be the more energy demanding networks. Yeah. Also, there is this energy colosseum that we can perform real-time energy measurement for LLM responses on your prompt. And we can see that so here we actually run inferences and which generates new text according to your prompt, and we model the energy. We measure the energy for how much it took to generate, say, certain text for this prompt across different models. Yeah, and all of these are online and open. Feel free to check it out, and you can have some potentially very interesting results. Yeah. For instance, sometimes larger models that you thought might be more energy demanding can actually be more energy efficient than smaller models. Yeah. And as you can see that the Zeus is already being used in different scenarios, and as an open source framework, the core value is Zeus. The core value of Zeus is generality. We want to make very clear trade-offs and give user full control over which trade-off point they want. And we also want to make minimal assumptions to workloads and GPU types. And whenever we make any, be explicit about them. And we want to be very general, be very generic, and so we are agnostic to hardware software environments. Yeah, we also plan to add AMD GPU support in the future. Now at the moment we focus on NVIDIA, but we want to support AMD as well.
Is there a fundamental difference between the architectures? Of course, the architectures themselves are fundamentally different, but in terms of spanning the space that you need to span in order to optimize it, is there a significant difference in how you would approach it?
The approach would be the same. The library would be different. So the optimizers, like the multi-unbounded design, all of this would be the same. But we basically, the place where we use NVIDIA management library, we need a counterpart of AMD library. That's pretty much the change. Yeah.
Mm-hmm. But you also have on AMD processors, for example, a power limit that you're able to specify on those, or is that an NVIDIA concept altogether?
Um, yeah, good question. Actually, I need to we need to take a look at the like I myself did not take a look at the AMD power configuration knobs. Yeah.
Mm-hmm. Okay,
We,
no, fine. Just something that came to mind. Thanks.
yeah. Good question. Mm, yeah. So, so paper is submitted and open source in like 2022, late 2022, and after that we done so much more, and we also started the website called the ML Energy Initiative, ML.energy, and it's a single place for disseminating all our past and recent and ongoing effort, and yeah, with and beyond the research artifact, we publish our open source framework as well, and yeah, there are some other follow-up works that our labs have been doing. Is one extend Zeus to optimizing energy to optimize for carbon, because so depending on the type of electricity that your data center runs on, like the same amount of energy may mean different carbon, right? And so there, in one of the hackathons, carbon hackathons, one of our some of our lab mates, they won second prize using uh, uh, framework called Chase. With framework called Chase, it sort of like applies the uh, takes in the carbon intensity, basically how much tons of carbon dioxide emitted per kilowatt hour of power into the count of DNN training, and did some optimization there. So sometimes you can move your computation to a more cleaner data center to reduce the carbon cost. And sometimes the carbon cost per electricity varies according to time, because at this moment maybe more of wind power, solar power is available if it's daytime, right? So there are some other factors that can come into place if we want to optimize for the carbon instead of energy. It's a lot more interesting factors, and yeah. Also, um, with the TLDR for that is that we can reduce like up to 14% less carbon for DNN training. And there are some other works that trying to dive deep into the model itself, and trying to sort of introduce additional frontier than the Pareto frontier. So the idea is that sometimes we can even improve the energy without sacrificing the training time. And we dive into models, we identify such thing we call energy bloat, and we can reduce that without affecting the training throughput. And one example is that when in especially in large language model training, a lot of the models, or a big part of the models, use something called a pipeline parallelism. The idea is that there are multiple stages and computation stages that are happening in a pipeline fashion, as you can see from the chart in the left. But so sometimes there is a critical path in this compute graph, such that like if we can increase the speed of the component of this graph, the overall training speed increases. But the other computation stages are not on the critical path. And for the things that are not on the critical path, what we observe is that, the GPU by default run as maximum power limit, right? And for the the stages that are not on the critical path, we can maybe slow it down a little bit to make it more energy efficient. Slowing those non-critical path component or the stages of the training would not affect the iteration time at all. So it's basically free energy savings without sacrificing the model training speed, if we can identify which part of the model are not on the critical path, right? yeah, it's a natural extension to our Zeus framework. And so you can see here the comparison that the new work Perseus, we can achieve, even better energy and training time trade-off. And more excitingly, most of the large language models, they use pipeline parallelism. So for the most energy demanding models, this technique works better. Yeah. So yeah. And at last, I'm just sharing some of the links that are related, and feel free to check them out. And yeah, that'd be all. Thanks.
Wonderful. As for the links, we can put those in the description of the video as well, so people can refer to those directly.
Yeah.
But great. I have no additional follow-up questions. Thank you very much for taking the time to go through the presentation. I really enjoyed it.
Thank you. Thank you for the invitation.